All right, so today we're going to start on the next module, which is strings. The reading that you're probably working on right now, though it's due on Monday, is all about strings, and so we'll continue that then. But just a quick aside here, since registration does open on Monday, the majority of you are probably freshmen, and so you're not going to be able to register right away. You might have priority registration like later in the week or the week after. I just wanted to make sure that everybody understands what the typical schedule is for computer science and computer engineering majors. If you're neither one of those majors, then you feel free, or you want to continue in computing, then this might be relevant as well. But typically what you take in your second semester is Computer Science 2, continuation in Computer Science 1, discrete mathematics, and this 1 hour Unix course. It's online, it's videos and stuff. You just learn some additional Unix programming. And then others, which I can't advise on at all, because that's entirely dependent on your own schedule. So now 235 is discrete math, so lots of proofs, lots of written stuff. I'm not involved with that this coming semester, but you can go ahead and ask your, other students about that. Now 156 is what I want to focus on because that is Computer Science 2. I'm currently scheduled to teach both of those sections. I just wanted to bring your attention to the fact that the lecture is, when is it? I know my schedule. It's Monday, Wednesday, Fridays from 10:30 to 11:20. There is an H section, by the way, and the H section is right after that, hopefully in the same room. Nope, just in the next door over, so I'm going to have to break down and go over there as well. But in any case, once we've graded all of our midterms, I'll be sending out some notices and invites to 156H. If you're interested in taking the H version of Computer Science 2, go ahead and talk to me. We'll find out if it's the right one for you. The difference is that we're going to assume, one of the main differences among others is that we're going to assume Java background. And so if you already have Java, or if you're willing to pick it up really, really quickly, then that might be appropriate. Otherwise, in the main section, we cover that. I'll talk about the actual course here in a second, but I did want to bring your attention to the fact that there is an in-person section, 150, and there's an online section. I have no idea what the 850. Oh, I know what that is now. That's the Big Ten Consortium. Do not register for that. If you want to register for the online version, there's the 700 version instead. But understand that they're the same course. The way that I run the online version is exactly the way that I run the online version for this course. That I live stream everything no matter what. Even if you're in the in-person section, there will be recordings available. There are pre-prepared videos. There's Zoom for office hours with LAs, and lab times are also online with Zoom as an option. So if you want to go for the in-person section and treat it like an online, like day-to-day, then you can do that as well. I only mention that because, and don't quote me on this, but I think that there is some difference in tuition for online courses. Yes? No? All right, then then I won't say what the difference is because I have no idea what the difference is. Look into it, talk to an advisor. Those are the courses that you'll probably be taking next semester if you're a major, right? Now, as far as the content of Computer Science 2 itself, you can go to my GitHub page that hosts everything. There's a nice textbook. The topics that we go through are an introduction to Java. So in the first 3 weeks, we introduce a new programming language, Java. And then we look at object-oriented programming with respect to Java. Then we get into SQL, which is database stuff. SQL is structured query language, so we design databases. We write queries to query against a database. And then we write Java code to programmatically connect to our database so that we can build a larger app. Then we get into data structures and algorithms at in the last third of the course. It is project-based. There are assignments that are due about they're not hacks, but there are labs. But there are like assignments that build on each other every 2 weeks or so. No exams, no quizzes for this. It's 100% project-based. All right. Questions on that next semester? So if you want more information at the end of the semester, I can provide it. Otherwise, that's several months away now, right? Okay. Just wanted to bring that to your attention. so that when it is time to register, you have at least a little bit of information. Hopefully you're getting other information from CS10. Ask questions there as well. Right? Okay, so in something that's a lot easier in Java next semester is going to be strings, but in C, strings are a little bit difficult to do compared to other programming languages, but you are already prepared to deal with strings because you already know about arrays. In C, strings are ordered sequences of ASCII characters. Right? Now, I am emphasizing the fact that they're ASCII characters. Right? There are alternatives. The ASCII text table, ASCII text table.com or whatever it is. Right? There's the ASCII text table. Yeah, it is .com. ASCIItable.com. If I zoom in on this, you'll see that it is restricted to A through F, capital, lowercase. We've looked at this before when we've looked at characters. This is basically what you can hope to achieve in C. If you want other things like CJK fonts, right? Chinese, Japanese, Korean fonts, or a list of CJK fonts, right? Stuff that looks like this, or emojis, or even ancient Egyptian hieroglyphics. You are using a different a system called Unicode, right? So not Unicode. Unicode uses a lot more bytes. Over here with ASCII, every character is exactly 1 byte. That's 8 bits. We can represent 0 through the extended ASCII character set here is 255. So with 1 byte, with 8 bits, you can represent 256 unique characters. Some of them are not printable, right? For example, you can make your computer ding, right? There's a bell. If you print out the character with an ASCII value of 7, it'll make your computer ding. Why would we have that? This was created back in the late 40s. What were they typing on in the late 40s? Typewriter, right? So what happens in the typewriter when you get it to the end? Ding, right? So they put that into the ASCII text value table because they thought that they would need it, right? And there's also a difference between a line feed going down and then just taking the drum on the typewriter and moving it up when you're stuck on the same line. That's a line feed versus a vertical, not vertical tab, but I don't know where it is. It's somewhere in there. But in any case, we're not always restricted to the ASCII text table. We can bring in a library. We can bring in an extension to take care of all those CJK fonts, to take care of all those emojis if you want to. And even VS Code supports it because it's 2022. But we're going to restrict our attention to the ASCII text values. Okay? In C, strings must be null terminated. They are arrays of characters. So character, and then you have a character array, unlike an integer array. If you've got integer array and you've got values 10, 20, 30, 40, 50, right? Instead of those integer values, you can hold characters. CHRIS, my name. However, at the end of every array of characters, you need what is called a null termination character, null terminated character. The null terminating character is ASCII value 0, and we write in code \0 to get that character. That's a very special character. Let's take a look at the ASCII text table again. Where is it? Right at the beginning. The very first character is the null. It's not null, as in like the pointer null. It is the null byte, the null terminating character. So we've got a new idea of nothingness here in C, right? We've got, do not confuse it with other things, right? It is not the value 0, right? Like, if I were to type int x is equal to 0, it's not the same thing, right? It is not the pointer null, right? That's completely different as well. Now, a lot of these things have an equivalency that you can get away with, but make sure that you're using them in the correct context, right? It is not void, right? It is not the end line character. If I want to go to the next line, what do I type? \n to go to the next line, right? It's none of those things. The end line, the null terminating character is \0. It is completely different, okay? And it is not any of those things. If a string does not have a null terminating character at the end, It is not a valid string. If you try to do anything with an invalid string, it is undefined behavior. Right? Anything could happen. Anything could happen, right? It could be a seg fault, right? It could be what's called a stack smashing event. It could be bad results. It could be whatever, right? It might not even show up as an error. Valgrind will find it though. So here's another tool that you can use for Valgrind. If you've got an invalidly non-null terminated string, then Valgrind can detect that. So what I want to do now is let's go over here, and first of all, let me load this up in the background while we type some code over here. Let's go ahead and create a string. So if I just created int array, right, and I set it equal to 10, 20, 30, 40, whatever. I'll just leave it as 3 things so I don't have to type too much, right? That's an array of integers. That's not a string. Right? That's a collection of integers. So let's now make a change here. First of all, I'm going to change the type. A string is an array of characters. Let me go ahead and say what this is. I'm just going to put my name in here, like I suggested before. Now, you can use syntax like this, but that's not what a string is. A string is going to be double quotes. There we go. There's my first string. Right? Now, how long is this string? How big is this array? In fact, sorry, let me go ahead and I'm going to fix something later on. I'm going to go ahead and put lowercase c here. CHRIS, 5 characters. But what is hidden at the end there? That is automatically taken care of by the compiler. It puts the null terminating character in there. So how big is this actual array? 5 valid characters and then 1 null terminating character at the end. Okay? To visualize this, let's go over here to our C visualization tool and look and see what this looks like. Okay? There we go. So, do you see it now? CHRIS, and at the very end, it inserts that null terminating character for you. It takes care of it for you. There are some operations later on that we'll look at that do not necessarily take care of that null terminating character for you, and you have to do it manually. Just like memory management, you have to, the responsibility falls to you. Knowing when and where and why that you need to put that null terminating character in there, unfortunately, it's just something that's what makes it difficult in C. In a programming language like Java, where you don't have memory management or anything like this, it takes care of all that stuff for you. But C is different. C, you're still responsible for this stuff. Okay? Let's print this out. Printf. So the placeholder for an integer is %d. The placeholder for a floating point number is %f. And the placeholder for a character is %c. What's the placeholder for a string? What do you think? %s. It makes sense. My name is, and then I'll go ahead and end the line, and I'll print my name. So, CSE 155E, GCC demo, and we'll see that it works here. Right. My name is Chris. Wait. All right. Lowercase c. I need to change that. Right. So let's go ahead and change it here and then print it out again. Oops. There we go. So how can I change that first character into a capital C to correct for it? It's an array, right? So how do I get the first element in an array? Index 0. Right? And what do I set it to? Do I set it to something like that? No. How do I specify single characters? With single quotes. So single quotes on C. Right? And we'll see that I'm going to print both of these out, the original string and the updated string, the change string. That tells you something about strings in C. They're mutable. Mutable means like mutation, organisms can change. Mutability in code means that data can change. In particular, this string changed. I changed it from a lowercase c Chris to an uppercase c Chris. I was able to change it. Now, if I put a const in front of this, what do you think happens now? Remember, we used the const keyword with respect to functions and arrays so that we can make the promise that this function will not change your stuff, right? So what happens here? Now it's immutable. It cannot be changed. And the compiler says, wait a second, you're changing it on line 13. You can't do that. Right? So by default, strings are mutable. You can change them. A lot of programming languages don't allow that, right? And a lot of programming languages, that's a good thing, right? Because immutability means that you have thread safety for free. When you've got multiple threads running on the same process or on different processors in the same process, right? In parallel, you can have tasks running in parallel, and you don't want them stepping on each other's feet. And if you've got immutability, then that means that one thread can't change what another thread is working on. It's a very good thing. Unfortunately, we don't have it here, unless we have the const keyword, right? And that's not always desirable. Right? All right, so you can change. You can change individual characters. Can you change the entire thing? For example, my full name is Christopher. Let's try it. Name is equal to Christopher. There we go. And then we'll print it out again. Right. So first of all, is that going to work? How big was the array again? 6, right? 5 letters, 1 null terminating character. Can you put something of this length in that array? I don't know, how many is that? 5, 6, 7, 8, 9, 10, 11 characters. 11 characters plus 1 more for the null terminating character. So 12 characters total. Is 12 characters going to fit into an array of size 6? Nope. And I was amazed and pleased in today's, in the morning section to find that indeed the compiler checks for this and says, no, you cannot do that, right? It's smart enough to do this because this is a static array, right? So no, you can't do that. In fact, if I turn on the wall flag, I should be able to do this, right? Oh, okay. Well, you can't do that at all. All right, well, I'll just go ahead and make this big enough. Right? What I've done there is I've changed this so that the array is of size 100. CHRIS fits in there along with however many null terminating characters you want. Let's take a look at the visualization of this. Let's edit this code. What's it going to look like now? It's going to be a much, much bigger array with only CHRIS at the front and then a whole bunch of null terminating characters at the end, right? So when it gets initialized, there we go, Chris, and then a lot of null terminating characters after. In other words, we've got room. We've got room to change this. Right? So I've made it big enough. Right? Let's go ahead and try to do this again. You still can't do it. This is not how things work in C. You can create an array and initialize it and assign it a value when you first start, but after it's been declared, you can't do that anymore, right? You can't reassign an entire value like this. Instead, so we cannot do this in C. Right? Many other programming languages allow you to do something like this, but not C. Instead, we need to use a function, ... The function that we're going to use is in a library called the string library. So I don't see a string library up here. We have a brand new library that we need to bring in. Guess what its name is? String.h, right? There. Right? Some things are named that make sense here. All right, so we need to use a function. The function I'm going to use is strcpy. What do you think that stands for? str is obvious, right? String. And then cpy is short for copy, right? I'm going to copy the contents of one string into another string. I'm going to copy into name my full legal name. There we go. And now when I do this, the compiler is perfectly happy, and in fact, it will run and print out my name, right? Because it's big enough. Now, if it's not big enough to hold CHRIS TOPHER, right? It's only size 6, then the compiler will still catch that, right? In fact, it'll tell you, you're trying to write 12 bytes, 11 characters in my full name, plus the null terminating character for 12, and you're trying to put it into a destination of size 6. You can't do that. Right? All right, so I'll go ahead and pump this up again, make it big enough, right? Because I want to do a bunch of other stuff with it too. Right? So instead, you need to use the function, strcpy. It copies the contents of the second string into the first string, right? It takes care of the null terminating character for you. But it is your responsibility to ensure that the destination string is big enough. Right? If it were not big enough, CHR to hold my entire first name, so hopefully the compiler will catch it in a lot of instances, but there are other instances in which it will not catch that. For example, this is a static array. Where is it allocated? Where's the Python tutor showing you that it's allocated? On this thing called the stack, right? It's inside this stack frame. We've seen this before. What if I tried to allocate something for really large data here? How many is that? 1, 2, 3, 1, 2, 3. 100 bytes, 100 million bytes, right? That's going to be just short of 100 megabytes, right? Is this even going to compile? Yes. Will this run? Segmentation fault. Can 100 megabytes fit into this small little box of main? Nope, that's your stack. Your stack is limited to about 8 megabytes. We looked at this when we were looking at arrays. If you try to fill that up and go beyond, what do you have? Your stack has, you filled up your stack glass, right? And what happens? You keep pouring water into it. It overflows, stack overflow, right? Even if it's of size, 1,000, you might want to rethink that, especially if you're working in an embedded system. Yeah, that's only 1K, but do you have 1K to spare on hardware where the chips are measured in 64K or something, right? Who knows, right? So I'll go ahead and kick it down to 100 here. The alternative is what? Or I'll keep this here for a second because we're going to want to work with it. So if you can't use static arrays, what's the alternative? Char star dynamic arrays. Right? Name. Now, to allocate enough space for my name, what do I need to do? Call, what's that function that we call? Malloc, right? The only difference here is that we're using characters instead. So in our typecast, we typecast it as char star. Over here, we ask for a certain number of bytes. So CHRISTOPHER plus the null terminating character, that's 12, right? Times however many bytes a char takes, size of char. Right? Now, on 99.9999% of the systems out there, a character is going to take 1 byte. Right? So you could get away conceivably with removing that and therefore removing the multiplication. It is that 0.00001% of the time that you're going to end up blowing it up. Right? So don't do that. It is best practice to always do this no matter what. All right? It also future-proofs yourself. If they ever do decide to integrate Unicode characters natively into C somehow, then suddenly now the character becomes 4 bytes instead of 1 byte, right? And all of your code will not break if you've done this. Okay? That'll never happen. Right? Trust me, that'll never happen. Right? All right, so let me go ahead and get rid of that for a second. And let's walk through this code now that I've dynamically allocated this instead. I'm about to print it. What's in that location right now? I have no idea. Let's go over to the Python, the visualization tool over here, and let's go ahead and replace that, right? And see what this looks like. Right? So we allocate it not on the stack, but where? On that other thing that's over there, the heap, right? And we've got room for any string of size, 12. Or of 11, sorry, right? Because we need that null terminating character over there. I'm about to print the contents of this array. What is that visualization telling you about the contents of that array? What default values does C have for any variables? Who knows? 0, dead beef, garbage, undefined behavior. I wonder what we'll print. It'll probably end up printing nothing. My name is nothing. Oh, nope. It didn't even like that, right? It's saying, wait, you didn't put anything into that array. I'm going to refuse to print it. I wonder what it would do over here. GCC. Run this. There you go. My name is what? Did you put anything in there yet? Nope. But we did put something down here, right? First of all, I changed it to C, and then down here I changed it to my full name here, which was just large enough to do that. Now the reason that I did this is, suppose we kick that down to 5. Is that enough to hold Christopher anymore? No. The compiler will not save me in this case because it's a dynamic array. Right? Oh, wow. Come on, really? Wow, you're working overtime. Good job. I can't believe that it knew that. Certainly if this were in another function. Oh, you know what? It's just a warning. Okay. So it is warning me. If I get rid of the wall flag, will it still warn me? Yep, it will. Awesome. Very, very good compiler. The compiler gets its brownie points for the day. Right? Very, very nice. But whether or not it works, I have no idea. A.out. Okay, it will work. Seemingly it will work. If I ran this through Valgrind, I would get all sorts of reported errors. Right? 24 errors. Right? Now, there's really just one error, right? It was an uninitialized string, but every time I printed a character, all 12 characters, printing 12 characters, that's 12 errors. Doing it twice is 24 errors, and that's where those errors are coming from, right? So my mistake here was thinking that this was a valid string, right? Simply just declaring this is not yet a valid string. Why is it not a valid string? Because there's no guarantee on what's in there. To make it a valid string, what I could do, make it a valid string. I could say that the first character here is going to be the null terminating character. Right? End it. Right? Now it's a valid string. Right? And let's pump this back up to 12 so that it works later on as well. It's a valid string here. Uh-oh. Is it a valid string anymore? I overwrote that null terminating character by putting a C in there. I can make it a valid string again by restoring that null terminating character. Right? Now it's a valid string for this print statement. It's still a valid string here because 12 is big enough to hold Christopher. Right? And when I print it down here, it's a valid string again. GCC, no errors this time, and Valgrind is more than happy about this. Yeah? It does. It does. It does take up a byte. Let's see. Edit this code. And strcpy. Let's go ahead and visualize it. In the name, Christopher. There we go. And visualize that execution. After it copies my name into that character array, you can see at the end, it has to be there. Right? It is 8 bits. It is 1 byte. It has to be there. So anytime that you create a string and you know, I need to hold a string that is n characters, how big of an array do you need to allocate? N plus 1, plus 1, plus 1, plus 1, plus 1 for every single allocation of every array for strings. Do not do that for regular arrays like integers and double arrays, because you don't need the null terminating character for that, right? They're not strings. Strings are different. Right? Okay. So I'll make sure that you've got this in the notes. And let's go up. So no need to answer. Okay. A question about the LA application deadline. I have no idea. I'm sorry. I didn't even know that they had opened it, or that they had closed it for that matter. I thought that they were in continuous hiring mode. So if there's an LA out there that's watching or wants to post a Piazza for the LA applications, please do so. All right. And I would encourage anybody in here that's doing well and wants to help other people do well in this course, go ahead and apply to become an LA next semester, a learning assistant. Right? Right. So strings in C. Right. Again. Oops. Did we already do this? Yep. All right. So to review. Right. So strings are arrays of character elements, char elements. In general, each char element is going to be 1 byte. Right? That's not always the case. But you can declare it using char and then provide a size, or char star, not int star because they're not integers, right? You can declare strings like we did above, right? We went through that. And string assignments. Again, you cannot use let's go with subsection here. Once you have created a string, you cannot reassign its value with the assignment operator, right? The equals operator, right? You must use the strcpy function to copy the contents of one string into another. Now, another way that you could do this, of course, is you could write 12 lines of code. Set the first one to C, set the second one to H, set the third one to R. Nobody does that, though, right? Just use the string strcpy function. It is located in the string library. The string library is string.h. Right? That's not the only one in there, and there are dozens of other string functions in the string library, and we will cover them as we go along, at least a subset of them. Right? The function has the signature. I'm just going to cut and paste this. There we go. Like this. All right, and let's go to the next line. There. Char star, don't worry about the return type there. But strcpy, and then it has a destination string and a source string. Right? So again, it copies from the source into the destination. Why is it like that? Why do we take the thing on the right side and copy it into the thing on the left side? Because it follows the same pattern as a regular variable. Int x is equal to 42. What are you doing? Taking the value on the right side of the assignment and putting it into the in the variable on the left side of the assignment. And that's what this does. It takes the source value and copies it into the destination value. Right? Some assumptions here. It assumes that the destination string is big enough to hold the source and its null terminating character. If that assumption is wrong, if you have not allocated enough memory, then that's a seg fault. That's a stack smashing event. That's a bus error. That's undefined behavior, right? It could be bad results. It assumes that the source string is a valid null terminated string. If it's not, the way that it works is by simply going along and saying, I'll copy the first character, I'll copy the second character, I'll copy the third character. How does it know when to stop? When it gets to that null terminating character, and then it copies over the null terminating character. What if there is no null terminating character? It'll just keep going. It'll keep going until it hits memory that doesn't belong to it, at which point you'll have a segmentation fault, hopefully. Right? Otherwise, you'll just have garbage values and you'll corrupt your own memory. Okay? Let's see. It does take care of the null terminating character for you. Now, observe the usage and lack of usage of the const keyword. We just reviewed that. What does it mean? It means you're not going to be making changes to it. There's a const in front of the source. What can you safely assume? That the source will not be changed. Do we have a const keyword in front of the destination? No. Its lack of a const keyword means that it will be changed. That's the whole reason for calling the function. We want you to copy the values stored in source and copy it over to destination for us. Right? Okay. Cool. So, yeah, that's all for now. 15 minutes left here. I'm going to go ahead and... Oh, here's another operation. String concatenation. Right? So concatenation means appending one string to the end of the other string. Right? So in this case, that means you can use the function strcat. Right? Again, you'll see a pattern here. Every string function is going to begin with str, and then what it does. CPY for copy, cat for concatenation, len for length, and a couple of others that we'll look at later. But you can use the function strcat. Okay, and here is the signature for that function. No, I'm going to have to modify it. So ignore it for a second here, and get rid of that, and get rid of that. We'll talk about those on Monday. There we go. str cat. There we go. So again, it appends the, and this is short now. Source is short for source. The contents of source to the end of dest. Right? Again, it assumes source is a valid null terminated string, and that destination, or dest in this case, is big enough to hold both the destination, both dest, source, and the null terminating string, for which it takes care of it for you too. If it is not big enough to hold that, then undefined behavior. So let's come back all the way over here, and what I want to do is I want to go back to the original declaration that I had here of name just being big enough to hold whatever I want to put into it. 100 for now. Right? And I'll go ahead and put in C. Well, actually, I'll just leave it like this. Right? And I just want to print my name at the end. I'm going to get rid of all the rest of this. Okay? It's already in the notes. Don't worry. All right, so I want my full legal name in this array now. To get it started, what do I need to do? strcpy into name, my first name, my first full legal name here, Christopher. There we go. Right. Okay. Now I want to put my middle name and my last name as well. If I did this, strcpy into name, my middle name is Michael. Right. There we go. Is that going to work? That's going to overwrite it. Let's see it. GCC. Oops, no, I don't want Valgrind. I just want to run it normally. There we go. My name is Michael. No, it's not. That's my middle name, right? So I can't use copy. What I want to do is I want to take the Christopher and I want to preserve that, and then I want to concatenate at the end of it Michael. So I use cat instead. And then my last name, of course. There we go. Now, is this going to print it exactly how I want? Is it going to print it out in a nicely formatted manner? Nope. It's going to print it all together, no spaces. So what could I do? I could do strcpy or strcat name a single space. That's a single space. This is not a. This is a single space, granted, but it's a character. It's not a string. Right? So if you want a single space as a string, double quotes with a single space. Then you can put 1, 2, 3. You can put as many spaces in there as you want. You can put tab characters in there if you want. I'm just going to go ahead and go with 1. Or an alternative would be to put the space in the actual string. Right? So GCC, a.out. Oops. Oh, what did I do? There. Not double quotes over there. There we go. And I can't believe you didn't catch that. You caught the other thing, but you didn't catch that thing. Right? That was even more obvious of an error for a compiler to catch than the other stuff. I have no idea why it didn't catch that. There we go. My full legal name is there. All right. Now, 100 is more than enough space to print that out. So what else is in that string at this point? Just a bunch of null terminating characters or garbage or whatever. Let's find out. Let's go beyond my name and find out what's in that array. For int I equals 0, I is less than 100, I plus plus. Print f name sub %d is equal to %c, and I'm also going to print out %d here, and I'll explain in a while, in a second here. I name sub I, and then int name sub I. There we go. So let's compile this and see what goes on. There we go. Let's go up to the top. There's my name, CHRISTOPHER. What do those numbers correspond to? 67. Let's go back to our ASCII table. Do you see 67 here? Capital C. Right? Do you see 104? What's that going to be? Lowercase h, etc., etc., etc. What about that space? 32. The space on the ASCII text table? 32, right there, space. Now, it doesn't print out the word space, right? Because if they left it blank, then it wouldn't be apparent that it was supposed to be the space, right? What else? Michael Burke, there we go. And then what do we have after that? Nothing prints, but the ASCII text value is 0 everywhere. Right? Don't assume that that's going to be the case. The only thing that you can assume is that by calling these functions on valid null terminated strings is that the one at the very end is going to be null terminated. Okay? One last exercise here. Right? So one common thing that you want to do is to copy strings. Let me go ahead and put this into the notes so I can get rid of it. Right. There we go. All right. So let's get rid of this. Say that I've got a string, char name. Let me restore my full name here. Christopher Michael Burke. There we go. And I want another completely different copy of it. Right. So there's name, char, full name. Right. And I want to copy, say, something like this. Right. Now, what kind of copy is this? Invalid initializer. Fine. I'll do it like this. Yeah, okay, there we go. And then let's print it out. Print out so that it would actually print something. Full name is equal to %s and the line. There we go. And full name, or just name. Name. There we go. Name. And full name. Right. So what's this going to print? Now it's no longer complaining that I'm not using those variables. It's going to print both of those. But what does that look like in memory again? Let me copy this and bring it over to Python, tutor, C tutor, whatever you want to call it. And let's visualize this execution. So that's a static array. It's going to be in this main over here, right, in the main's stack frame. Next, next. Now I'm going to make full name equal to name. What's that going to do? It's a pointer. It ends up pointing to the same thing. There is only one string here, and I've got two references to it. Do you remember what kind of copy that was? Shallow copy, right? So when I make changes to one name, right? Maybe, for example, my name, I only want the first 5 characters, right? So what I'm going to do is I'm going to cut it off as equal to the null terminating character here. What did I just do there? CHRIS, and then I made the 6th character at index 5 into the null terminating character. I truncated it. Right? It's not really truncation. Sure. We'll use the same word there. That word is actually used in databases for this kind of stuff. So we can. It's not an abusive terminology. We cut it short, right? Terminology. Right? All right. So now they're both affected. Why? Because when I make that change, it's reflected on both of these things. Right? So visualize this execution and run through it. And you'll see, but because they're pointing to the same thing, they refer to the same thing. Come on. There we go. When I change it for one, it's changed for both. You see it right there? The rest of the stuff is still there, right? I didn't change that. But as far as the string is concerned, it ends right here. Right? I don't want that. I want the other kind of copy. So if this is a shallow copy, what's the other kind of copy? Deep copy. So let's do a deep copy instead. ... First step is to make sure that you have enough space to hold whatever you're trying to copy. Right? We want to do a deep copy of my name up here. Right? So I'm going to call Malik. Malik. But I need to determine how many bytes I need. Well, first of all, size of char, right? The number of bytes that each character takes. But how many characters? So 1, 2, 3. No, I don't want to do that. I want a tool to tell me how many characters are there. strlen. What do you think that stands for? String length. Right? tell me how many characters are in that that string there. Right? It'll go through and count up all the characters. What it will not count, however, is that null terminating character right there. So this will be one less than you need. What do? Add one. There. So whatever I need to hold Christopher Michael Burke, I think it's, what, 26 or something like that, plus 1 for the null terminating character. Now, did that get the job done? That only created memory for it. So I now need to strcpy into full name, my name. Now, changes to one are not going to be reflected in the other because it's a deep copy. I should have the original in full name and name over here in Chris. Let's see that visualized as our last step for the day. Edit this code. So this is a retread of deep versus shallow copies with respect to strings, right? All right, so go through this. All right, so there's the initialization. There's my full name there. It looks like it was 26, right? And then the null terminating character at the end, so 27 total. Then we go ahead and create a brand new string, completely different copy on the heap. We use strcpy to copy it, and now it has the original, so that when I go to change it on line 9, I'm only changing this one over here. This one is unaffected. It's still T, and my full name over here. So that when it goes to print it out, we get both of those results. Gee, that feels like such a useful kind of functionality. Maybe there's a function in the string library to do it for me. Deep string copy instead of strcpy. Maybe there's something in there to do a deep string copy into full name, name. Compiler, you tell me. Is there such a thing? No, not at all. Right. But you can write it. So over this weekend, go ahead and take what I just showed you, generalize it, and put it into a function. You're going to want to use that function a lot in the coming weeks. Right? Because what is a string good for? It's good for data. And if you want to go and process data, you're probably going to be changing that data. Whereas you probably want an original copy that you're not screwing up, that you're not changing, so that you can retain that data, right? If you're going to process data and change it, do it on a copy so that you retain the original. Right? Deep copies are the only way of doing that. Questions? Oh, okay. So somebody not in the class. Just saying hi. Hello, YouTubers. Right. All right, then. I'll have a good weekend.